Hello. The goal of this video is to carefully step through the chemistry of what is happening during the titration of a weak acid with a strong base. That's what I'll be doing in the next procedure and results video. So let's first describe what that setup is going to look like. A couple of vocabulary terms as well to introduce here. The titrant is what's added very slowly and carefully to cause a reaction in a beaker. And here the titrant is 0.5 molar sodium hydroxide. So we'll be adding it to 20 milliliters of 0.1 molar acetic acid, and that beaker is also going to contain a small amount of the bromocresol green indicator. Typically, titrations are all about really careful volume measurements. We often use a burette tube, which is a very careful measuring device. I'm not going to be using the burette tube in the procedure and results video because my goal is not to quantify anything about the acetic acid. The only purpose of titrating the acetic acid here is for its buffering capacity. And what I mean by that is, you recall how frustrated I got last time when I tried to do this without any buffering. The pH jumped up so quickly when I added sodium hydroxide that it was really hard to see that speciation change from the yellow acidic form of the bromocresol green indicator, the HBG, protonated form, to the deprotonated form. So by having this buffering capacity here, we're going to be able to transition the indicator really slowly and carefully, see varying shades of green, hopefully, and very slowly change its speciation so that we can also take UV-vis spectra of the indicator. So let's think about what's happening at the molecular level. So I have a whole lot more acetic acid in the beaker than I do indicator. And the acetic acid is an acid. It dissociates, it loses its hydrogen ion, and that's governed by an equilibrium reaction and an equilibrium constant. Throughout this video, I'm going to be using the shorthand HA for the acetic acid just to make it simpler on my picture here. So HA is representing that protonated form of acetic acid, and it dissociates into acetate A- and hydrogen ions, and that equilibrium constant is 1.8 times 10 to the minus 5. So that indicates, that's a small number, it's a small value. That indicates that when I just have acetic acid and water, like I do at the beginning of the titration, it's mostly in that HA form. So I've only shown a couple, or a single acetate and hydrogen ion. The indicator, as you guys learned last time, is also a weak acid, so it can also dissociate. We don't know its Ka. That's the whole point of this lab, is that you guys are going to figure out what that value is experimentally. But we do know that if we're starting at a pretty low pH, which you would assume, since we're starting with a solution of an acid, that it's in the yellow form. So yeah, the pH is going to start out around 3.2 maybe or so. So that indicator will be in that protonated form, HBG, and it'll have that yellow color to it. Now, the titrant is a strong base, so there's no equilibrium here when we've just got sodium hydroxide dissolved in water. It fully dissociates into sodium and hydroxide. So when we first start adding it, let's think about what happens. We know that sodium hydroxide, first off, is going to dissociate into sodium and hydroxide. And we know that the hydroxide, as a strong base, is going to neutralize the strongest acid that's present there. So it will neutralize the free hydrogen ions, or really they're in the form of hydronium. So we should start seeing a pH increase right away as we neutralize free hydronium and convert it to water molecules. But there's not that many of them. So as we continue to add sodium hydroxide, we should see that hydroxide now neutralizing other acids that might be present. So let's think about what happens with the acetic acid. If we have hydroxide, which is a strong base, accepts hydrogen ions very readily, it'll pull that hydrogen ion right off the acetic acid molecule. what happens with that reaction? Our products are the acetate ion, because we've just removed that hydrogen, and neutralized water. So I now have that in my beaker as a product of that neutralization reaction. As we continue to add some more sodium hydroxide, some more of the same. We should neutralize more acetic acid molecules. We do have a lot of acetic acid molecules in this beaker. So yeah, we'll see additional neutralization of those guys. And eventually, at some point, you might be saying, hey, what about those indicator molecules? They're weak acids as well. Yeah, we would expect, depending on the relative strength of the weak acids, between comparing acetic acid and the indicator, we would expect that indicator molecule to also undergo neutralization. What happens in that reaction? Same thing. We're stripping the hydrogen off of that HBG molecule. But this time, we should be able to see something fairly visible, right? Because when we convert the HBG to the deprotonated form, Bg minus, it's blue. So now I've got a couple of my indicator molecules still in the yellow form and one of my indicator molecules in the blue form. So I'm kind of more slowly and carefully doing that conversion, and our eyes will probably perceive that as something in between yellow and blue. Let's continue to add some more sodium hydroxide, some more of the same. I can neutralize my acetic acid, I can neutralize my indicator. Remember, the indicator's out there at a much smaller concentration, so most of our titrant is neutralizing acetic acid, converting it to acetate, converting the indicator to Bg minus, and so on. So I'm going to add 4 more molecules here just to almost finish my titration, essentially, and continuing to convert acetic acid to acetate, and then my last indicator molecule is going to be converted to that blue form. Now our eyes visually, if this is a microcosm of a larger beaker, if we've converted all that indicator to Bg minus, now we should be at that blue stage. But it's going to be a much more gradual transition than you guys saw in the last video. Thinking again back to what pH looks like. I mentioned that at the very beginning there was some free hydronium from the dissociation of acetic acid. So we see a bit of an increase in pH at the beginning. But once we get past that point and we're neutralizing those acetic acid molecules, our pH is not changing very drastically. As we go through this whole large volume of titrant added, my pH is staying right around 4.75. That's what I'll expect to see when I do this titration. And that pH is related to the Ka value. I'm not sure if you guys have gone over this in class yet, but the pKa for any acid is a really important value. The P here is just like the P in pH. It means the negative log of. So the negative log of acetic acid's Ka is 4.75. And so around that pH, I'm converting my acetic acid molecules to acetates. I'm not really influencing the hydroxide or hydronium ion concentrations. So my pH is relatively stagnant for some time. And yeah, this is called the buffer region. So I'm very gradually changing my pH. I'd like you guys to think about what you would expect. The way this lab is set up, if I've set it up to kind of be able to gradually change that indicator color, gradually convert that HBG to Bg minus, I want you guys to try to think about what the pKa of the indicator, if it relates at all to a graph like this. This is the graph for the acetic acid molecule. Now eventually, once I neutralize all of or most of those acetic acid molecules, when I run out of them, then we see something very similar to what we saw in the first titration in this lab. A very steep pH increase over just a small volume. Yeah, when we run out of that buffering capacity, pH jumps up really, really quickly. So I think this will be helpful for you guys in understanding what's happening in the next procedure video. So yeah, hope you enjoyed it.